Glad to welcome everyone back to our channel, and today's video will be dedicated to the physics of elementary particles. We will try to understand what these very elementary particles are, how they resemble each other and how they differ, into what types and classes they are divided, and what roles certain particles play in our universe. This is already, if my memory does not fail me, the fourth attempt to make such a video. And the previous ones ended in failure because the material turned out to be too voluminous. Nevertheless, such a video is still necessary for our channel because in other videos, we quite often mention certain elementary particles, and it would be good if my dear viewers at least roughly understood what is being discussed, how bosons differ from fermions, leptons from baryons, hadrons from mesons, and so on. Therefore, on this peculiar tour of the world of elementary particles, we will still embark, although I will have to limit myself in the presentation of the material. We will talk only about what happens in the world of elementary particles, but we will hardly dive into the question of why it happens this way. Your whys on this matter you can always leave in the comments under the video. All such particles are divided by physicists into two large classes, which can very roughly be called specks of matter and droplets of energy. Droplets of energy are more scientifically called interaction carrier particles, or, which is the same, quanta of fundamental fields, electromagnetic, strong nuclear, and so on. We have already repeatedly discussed what is meant here, using as an example electromagnetic interaction, which consists of exchanging interacting particles by photons, transferring from one particle to another energy and momentum. That is, the photon is the interaction carrier particle of the electromagnetic interaction and the quantum of the electromagnetic field. Other fundamental interactions, such as strong and weak nuclear interactions, also have their own carrier particles. There should be something similar for gravity, but how exactly this something might look, we still understand quite poorly, since we have not yet managed to quantize gravity according to the general rules of quantum field theory. All carriers of fundamental interactions have something in common. Their spin, that is, intrinsic angular momentum, is equal to 1. On the other hand, all specks of matter have spin equal to 1/2. In physics, particles with integer spin are called bosons, while particles with half-integer spin are called fermions, and therefore carrier particles are often generally referred to simply as bosons. This is not entirely correct. Yes, all quanta of interactions are indeed bosons, but not all bosons are quanta of interactions. For example, composite particles of matter consisting of an even number of components with half-integer spin will also have integer spin, thus being bosons. Classic examples of such composite bosons are, for instance, the nucleus of a deuterium atom consisting of one proton with spin 1/2 and one neutron with spin 1/2, or the helium-4 nucleus consisting of 2 protons and 2 neutrons. To avoid confusion, interaction carrier particles are also often called gauge bosons. So there exist 3 groups of gauge bosons for each of the 3 presently quantized types of fundamental interactions. We have already talked about the electromagnetic interaction and its carrier particle, the photon. The photon has neither mass nor electric charge and is a so-called truly neutral particle. That is, a particle which is its own antiparticle. The carriers of strong nuclear interaction are particles known as gluons. They also have neither mass nor electric charge, but possess a characteristic known as color charge, something like electric charge, but for strong interaction. However, while in electromagnetism there is only one type of charge, which can be positive and negative, in strong nuclear interaction there are as many as 3 types of charge. A composite particle with neutral strong charge can be obtained in 2 ways, either by compensating a given type of strong charge with a charge of the same type but opposite sign, or by combining 3 charges of different types. The latter method is very similar to how red, blue, and green colors together produce neutral white, and precisely due to this analogy, the strong interaction charge is called color charge, and the entire modern theory of strong interaction is called quantum chromodynamics. I think it need not be said that all this has nothing to do with real colors. These are just names given by analogy with what we observe in the macroscopic world around us. So then, each gluon has two charges, one of which has a positive magnitude, and the other a negative one. For example, a gluon may have a positive red charge and a negative green charge, or, as physicists say, anti-green. There can also be other options, for instance, red anti-red gluon, green anti-blue, and so on. In total, 9 options. In reality, there are not 9 types of gluons, but 8, because real gluons are so-called linear combinations of such simple color-charge pairings. For example, the so-called gluon G1 is a symmetric linear combination of red anti-blue and blue anti-red gluons, meaning that if we ask the question of what color charge such a gluon has, we will get either red anti-blue or blue anti-red with equal probability. And there can be exactly 8 such combinations, not 9, due to special reasons related to the symmetry of quantum chromodynamics. But we have probably gone a little too far. Let us stop at the fact that there exist 8 gluons in total. The weak nuclear interaction, responsible for mutual transformations of particles, has 2 types of carriers, which physicists, without overcomplicating things, named W and Z bosons. Unlike other interaction carriers, weak nuclear interaction bosons have mass. For the Z boson, it is 1.6 times 10 to the power of negative 22 grams. For the W boson, it is 1.4 times 10 to the power of negative 22. More precisely, in physics, instead of mass, energy at rest is more commonly used, equal to mass multiplied by the square of the speed of light. For W bosons, it is 80 times 10 to the power of 9 electron volts, and for the Z boson, it is 91 times 10 to the power of 9. We will also follow this tradition, so when we measure mass in electron volts, which is a unit of energy, do not be surprised. W bosons also have an electric charge, which in absolute value is equal to the charge of a proton and an electron and can be either positive or negative. Positively charged W bosons are also called W plus bosons. Negatively charged W bosons are their antiparticles. The electric charge of the Z boson is 0, and it is a truly neutral particle, just like the photon. And also, among elementary bosons, there is perhaps the most famous elementary particle in physics, the Higgs boson. It is the quantum, that is, the elementary portion of the so-called Higgs field, the interaction with which we perceive as the mass of elementary particles. The Higgs boson has no electric charge, and its mass is 125 times 10 to the power of 12 electron volts. It is also a neutral particle, meaning it is its own antiparticle. At the same time, the Higgs field itself is not considered by physicists to be a fundamental interaction, but rather part of the unified electroweak interaction. And the Higgs boson is not commonly referred to as a gauge boson, since classical gauge bosons are quanta of vector fields, while the Higgs field is scalar, meaning that the spin of the Higgs boson is not 1, as in gauge bosons, but 0. So among all droplets of energy, the Higgs boson stands apart. Thus, the class of elementary bosons is currently divided into 4 groups of particles: the massless and uncharged photon, 8 gluons, massive W and Z bosons, and the Higgs boson. Now let's move on to matter particles. As I have already said, all of them have spin of 1/2 and therefore are fermions. And all these particles are divided into 2 groups, depending on whether they participate in the strong nuclear interaction, the very one that binds protons and neutrons together in atomic nuclei. Elementary particles that participate in the strong interaction are called quarks. There are a total of 6 types of quarks, which are named U, D, S, C, B, and T. These names have explanations. For instance, U quarks are also called up quarks, D quarks are down quarks, S quarks are strange quarks, C quarks are charm quarks. The 2 heaviest quarks have 2 different name origins. The B quark's name sometimes comes from the English word bottom, or sometimes from the word beauty. The T quark is called either the true quark or the top quark. These names mean absolutely nothing, just as the word quark itself carries no hidden meaning. As in German, it literally means curd. At that time, physicists were regularly discovering and inventing so many new things that had to be named that they simply gave up on coming up with elegant, intelligent names and started naming things however they pleased. Depending on charge, all quarks are divided into two groups with 3 in each. Quarks with charge of plus 2/3, such as U, C, and T quarks, and quarks with charge of negative 1/3, such as D, S, and B quarks. Alternatively, one can think in reverse and divide quarks into 3 groups, which are also called generations. First-generation quarks are the lightest U and D quarks. Second-generation quarks are the heavier C and S quarks, and third-generation quarks are the B and T quarks. It is easy to see that the quarks of the next generation resemble those of the previous one in all aspects, but have greater mass. Additionally, each quark has an antiquark with the same mass and opposite charge, bringing the total number of quarks to 12. Quarks naturally possess a color charge of one type or another. Quarks have a positive color charge, while antiquarks have a negative one. However, the color charge of quarks behaves differently than, for example, their electric charge. What electric charge a quark or any other particle is an intrinsic property of that particle itself. In contrast, the color charge of a quark can change over time. The same quark, within a very short period, can be red, green, and blue. One of the most interesting features of quarks is the so-called confinement, the fact that quarks cannot exist alone but must always be part of more complex structures. The reason for this lies in the specifics of the strong nuclear interaction, and in particular in the fact that the carriers of this interaction, gluons, themselves have color charge and participate in the interaction. We discussed in more detail why this happens in one of our past videos, and I think we will discuss it again in a video specifically dedicated to strong interaction, quarks, and gluons. But for now, as agreed, we will talk about what happens rather than why it happens. And it happens in such a way that quarks must form complexes that in total are colorless, meaning they do not have a color charge. As we have mentioned, there are 2 ways to do this. Take a quark and an antiquark, possessing color and anticolor respectively, or take 3 quarks, or 3 antiquarks, of different colors, or anticolors. The confinement rule does not apply to the most massive T quark, which does not participate in the formation of quark complexes, but not because it does not want to, but simply because it does not have time. On average, just 5 times 10 to the power of negative 25 seconds after its formation, it decays, and in its ultra-short lifetime, it simply does not have time to combine with other quarks into composite particles. Complexes formed from quarks are collectively called hadrons, from the Greek hadros, strong, in the sense that these particles are formed through strong interaction. Hadrons consisting of 3 quarks are called baryons, from the Greek word baries, meaning heavy, while hadrons consisting of a quark and an antiquark are called mesons, meaning having an intermediate mass between baryons and the lightest particle known at the time, the electron. Depending on the quark composition, the electric charge of baryons can be -1, 0, +1, or +2. Mesons can have an electric charge of -1, 0, or +1. By the way, mesons, consisting of 2 quarks with spin of 1/2, are bosons because depending on the orientation of the quark spins, their total spin will be either 0 or 1, meaning it will be expressed as a whole number. Meanwhile, bosons composed of 3 quarks will be fermions, just like the quarks themselves. The most important role in the world around us is played specifically by baryons. As the science called combinatorics teaches us, there are a total of 216 ways to assemble a baryon from 3 quarks of the 6 existing types. In reality, we currently know about 120, which is almost half as many. This is because many baryons turn out to be so unstable that we have almost no chance to detect them. Moreover, some baryons observed in nature are a superposition of several quark states. The names of baryons usually consist of a Greek alphabet letter and the suffix baryon or hyperon. For example, the aforementioned delta baryons, lambda baryons, sigma and omega hyperons, and so on. The names of mesons are formed according to a similar scheme, only using letters not only from the Greek alphabet, but also from the Latin alphabet. For example, pi mesons, k mesons, rho mesons, phi mesons, b and d mesons, and so on. In this particle zoo, it is easy to get confused, but there is no need to be afraid. The vast majority of them are usually dealt with only by narrow specialists. And in everyday reality, the overwhelming majority of these particles are unstable and exist for only an incredibly short time, transforming into increasingly lighter hadrons through the decay of the quarks from which they are composed. The only stable baryon is the lightest of them all, the proton, composed of 2 U quarks and 1 D quark, which simply has nowhere to decay. The almost stable neutron, consisting of 2 D quarks and 1 U quark, has an average lifetime in a free state of just under 15 minutes, after which one of the D quarks transforms into a U quark, and the neutron transforms into a proton with the emission of an electron and an electron antineutrino. For comparison, baryons containing the lightest of the heavier generation quarks, the S quark, live no longer than 10 to the power of -10 seconds, while baryons composed of heavier quarks have even shorter lifetimes. By the way, a very logical question may arise here. Why is the proton stable? And why is it precisely the proton that turns out to be stable? Indeed, would it not be energetically favorable for its D quark to transform into a lighter U quark? Yes, such a transformation would indeed be energetically favorable if we consider quarks by themselves. But the point is that quarks do not exist on their own, and for a quark complex, such a decay is energetically unfavorable. As a result of such a decay, a particle consisting of 3 U quarks would be formed, with charge of +2 and rest energy of 1,232 megaelectronvolts, compared to 938 megaelectronvolts in the proton. Why is the mass of the delta++ baryon consisting of 3 U quarks greater than the mass of the proton? The fact is that the mass of hadrons is determined not only and not so much by the mass of the quarks that make them up, but by the energy of their interaction inside the hadron, according to Einstein's equation E = mc². And it turns out that in the delta++ baryon, this energy is significantly higher, at least because it has charge of +2, and its quarks experience stronger electrostatic repulsion from each other. Although this is not the only or even the main reason. This means that the total rest energy and mass of such a particle will also be greater, and the lightest possible combination of 3 quarks is precisely the proton. In addition to baryons and mesons, there are also more complex quark structures, such as tetraquarks, composed of 2 quark-antiquark pairs, as well as pentaquarks, consisting of 4 quarks and 1 antiquark, a kind of baryon plus meson. These structures are extremely unstable and have an incredibly short lifetime. So elementary particles that participate in the strong interaction are called quarks. There are 6 types of them, plus 6 types of antiquarks. In nature, quarks do not exist alone, but only in the form of quark complexes called hadrons. Baryons composed of 3 quarks and mesons composed of quark-antiquark pairs, as well as exotic forms like tetraquarks and pentaquarks. The vast majority of hadrons are unstable, and only U and D quarks in the composition of protons and neutrons can exist for any significant length of time. And that is precisely why protons and neutrons account for most of the mass of the matter familiar to us, which physicists therefore also call baryonic matter. By the way, a question may arise. Where do higher generation quarks and the hadrons composed of them even come from? Most often, they materialize simply from the vacuum in quark-antiquark pairs in the presence of strong energy fields, whose energy is converted into the mass of quarks according to the formula E = mc². For example, this happens in particle accelerators, the most well-known of which is the Large Hadron Collider. In it, the kinetic energy of these charged particles, accelerated to nearly the speed of light, serves as the raw material for pair production and is released at the moment of their collision. In the same way, of course, not only quarks, but any elementary particles can emerge from the vacuum. Essentially, accelerators are primarily special factories for producing massive particles that would otherwise be impossible to study because they exist for an incredibly short time and are practically never found in nature. In nature, higher generation quarks and other massive elementary particles are born, of course, only very briefly, in various high-energy events. For example, when cosmic rays collide with atomic nuclei in Earth's atmosphere, during supernova explosions and in other similar processes. Particles that do not participate in the strong interaction are collectively called leptons, from the Greek word leptos, meaning light, since leptons are generally lighter than hadrons. All leptons are divided into two subclasses, charged and uncharged. A classic example of charged leptons is the electron, as well as its antiparticle, the positron, which has the same mass but an opposite electric charge. In addition, the electron has heavier siblings, the muon with approximately 200 times greater mass at 105 megaelectronvolts, as well as the tau lepton with a mass of 1,777 megaelectronvolts. Massive charged leptons also tend to undergo decay. For example, a muon, on average, transforms into an electron after 2 millionths of a second. The tau lepton lives even less, about 1.5 10 billionths of a second, transforming either into an electron or into a muon, which then transforms into an electron. Charged leptons of different masses behave very similarly to how quarks behave with their 3 generations. And what is most surprising is that leptons also turn out to have 3 generations. We do not yet know whether this is a simple coincidence or whether there is some fundamental pattern behind the 3 generations of fermions, the essence and meaning of which we have yet to decipher. In addition to charged leptons, there are also uncharged leptons of 3 generations, which we call neutrinos. We had a separate video about them, so here we will repeat only the main points. Neutrinos have no charge and have an extremely small mass, and some scientists believe that neutrinos should have no mass at all. Neutrinos arise in reactions associated with the creation or disappearance of charged leptons. To understand how these reactions proceed, it is useful to introduce a characteristic called the lepton number, which is equal to +1 for each lepton, whether it is a charged lepton or a neutrino, and -1 for an antilepton or an antineutrino, and then require that the sum of lepton numbers remains constant before and after the reaction. For example, in the reaction of beta decay, that is, the transformation of a neutron into a proton, the lepton number before the reaction was 0. During the reaction, an electron appears, meaning the electron-lepton number increases by 1, which should not happen, so an electron antineutrino with an electron-lepton number of -1 must also appear. If the electron is absorbed by a proton, as occurs in electron capture, then the electron-lepton number decreases by 1, and to compensate for this, an electron-neutrino must appear. The decay of a muon into an electron leads to a decrease in the muon-lepton number by 1, but an increase in the electron-lepton number by 1. So such a reaction must also produce a lepton-neutrino and an electron-antineutrino. Thus, we have 3 charged leptons, the electron, muon, and tau neutrino, as well as 3 uncharged neutrinos, the electron neutrino, muon neutrino, and tau neutrino, making 6 in total, and together with antiparticles there are 12. So it's time to summarize. All particles are divided into matter specks or fermions and droplets of energy, quanta of fundamental fields, which are bosons, that is, particles with integer spin. At the moment, 4 types of bosons are known: the photon, 8 gluons, W and Z bosons, as well as the Higgs boson, 12 in total. Matter particles are divided into quarks and leptons depending on whether they participate in the strong nuclear interaction. There are 6 types of strongly interacting quarks, but they do not exist separately and only appear within particles known as hadrons. Hadrons, in turn, are mainly divided into baryons composed of 3 quarks and mesons composed of 2 quarks. There is a vast number of baryons and mesons, but only protons and neutrons, made up of the 2 lightest types of quarks, U and D, are more or less stable. Leptons, which do not participate in the strong interaction, are divided into the charged electron, muon, and tau lepton, which take part in electromagnetic and weak interactions, and the uncharged neutrinos, which participate only in weak interactions, in which all fermions are involved. In total, there are 12 fermions, the same number as bosons. However, if we count antiparticles separately, the symmetry is broken, and there are 24 fermions and 13 bosons. The set of ideas about elementary particle physics that we have now briefly examined is known as the Standard Model. It describes all the elementary particles currently known to us, although we are almost certain that there must be more beyond these particles in the universe. For example, there are no suitable candidates for the famous dark matter. And in addition, the existence of particles beyond the Standard Model is suggested by many other current physical theories, which we will definitely discuss, but in one of our future videos. That is all for today. Taking this opportunity, I want once again to thank the sponsors of our channel here on YouTube, as well as on our pages on Patreon and Boosty, and invite everyone who enjoys what is happening on our channel to also make a contribution to the development of the project. All the best, dear friends, and see you again in our future videos.